The problem with the rectangular pulse shape is that its spectrum is very wide. From time frequency duality, we know that any signal that is narrow in time domain is wide in frequency domain. Rectangular pulse shape is very compact. So in frequency domain it has high side lobes, which is not only against government regulations for a particular band, but also allows excess noise and interference to enter a system. What is required is a pulse that is extended in time domain. So what we do is that we expand the pulse shape. Instead of making it a rectangular pulse, we expand it, and when we expand it, it creates inter-symbol interference for the neighboring symbols. Intuitively, how can we avoid this inter-symbol interference? We make a condition that the autocorrelation of this pulse shape should pass through zeros when it reaches the other symbol value, the integer multiple of symbol times. That's how we put it. And when this does that, we say that Nyquist-No-SI criterion is satisfied, which says that the autocorrelation of the pulse shape should be 1 at the current symbol time and 0 for all other symbol times. If you don't understand the equation, I hope that this concept is clear from the figure. This is the autocorrelation of the rectangular pulse shape, the triangular one, and you can see that we have another pulse shape that is varying smoothly in time but passing through zeros as integer multiples of Tm, thus causing no ISI. Going towards a practical pulse shape, we know that the problem was that very wide and slowly decaying side lobes. So we want to compact the spectrum, and when we compact it, we make it a rectangular spectrum in frequency domain, not time domain. Now this is impractical. So what we do is that we say we can increase its bandwidth by some factor by convolving it through a spectral lobe. Imagine this shape sliding through the rectangular pulse shape. So it creates this smooth transition on both sides. This extra width which comes from this resulting convolution in frequency domain during our pulse shape design procedure is called excess bandwidth or roll-off factor. For example, raised cosine spectrum is the most common name you would have heard. A raised cosine formula is given by this, the pulse shape is given by this, but the main concept is the same. This comes from the convolution of a rectangular spectrum through an even spectral lobe. So for a general alpha, where alpha is the excess bandwidth, we have this formula, and you can see the symmetry around over 1 over 2 Tm and minus 1 over 2 Tm. When you go to time domain to find its impulse response, we can clearly see that the spectrum with low values of alpha has high lobes in time domain, and the spectrum with large values of alpha has low side lobes in time domain. Because of this, if we have a timing synchronization error, there is less inter-symbol interference. We will see that concept later. Question now arises is that where should we place this smooth raised cosine pulse shape? One solution is that we place it at the receiver, but the problem would then be that the spectral leakage at the transmitter cannot be controlled. We can put it at the transmitter, but then extra interference and noise will be entering the receiver system according to the bandwidth of the pulse. So a solution is that split the pulse into two parts. Put one at the transmitter and the other at the receiver as follows. So we have the spectrum like this. We split it into two parts, PF into P conjugate F, PF magnitude squared. So when we take the under root, we have the pulse shape which is the square root of this. So that's why it's called, this is the raised cosine, and we call square root raised cosine, where the square root is taken in frequency domain, and from using an inverse discrete Fourier transform we get the impulse response of this square root raised cosine, and that is the pulse shape which is used in pulse shaping procedure of a PAM, pulse amplitude modulated system. There are other better pulse shape, but this one is most commonly used. Let's look at this very interesting figure. So this is pulse number 1, pulse number 2, pulse number 3. You can see that they are all passing through a point where there is no inter-symbol interference from the other pulses. So when this pulse reaches its peak value, every other pulse is going through 0. Even this one, if you see the contribution long far enough, you will see that it's passing through 0. The consequence of this is that when you modulate these pulses, then we have -1 +1, -1 +1, -1, and so on. And at the receiver we have correct timing synchronization, and when we sample the signal right at this point, there is no intersymbol interference at each instant and the symbol value comes unharmed. In GNU Radio, for example, we have a root raised cosine filter block in GRC. The actual utility is FIR-DES, which designs windowed FIR filters, which has a member function root raised cosine, and here are the arguments. Sampling frequency, we already know that. Symbol rate, the relationship between the two is defined by L, number of samples per symbol. So this symbol rate is Fs over L. Alpha is the excess bandwidth we have discussed so far, and taps is the number of taps in the resulting root raised cosine impulse response. There are different methods to select the value of gain for different purposes. This is the time to revisit pulse amplitude modulation, which was discussed in the context of a rectangular pulse. So here we can see the bits are generated, and according to which we have the transmit symbols. The transmit symbols are upsampled by inserting 1 0 in between two samples, which means that the upsampling factor L equals 2. After which the pulse shaping filter smoothes out these transitions. The received signal is contaminated with noise. Therefore, after the filtering, we do not have exact symbol values, but if the SNR is high enough, the values will be pretty close. So if you see every second sample, because L was 2, is close to our symbol value. We downsample by 2 to get the symbol rate sequence, and then we map it to a constellation for detection. Minimum distance rule implies if it's 0 greater than 0, the value is plus A. If the falling sample is less than 0, the corresponding symbol is minus A.
Having covered the pulse amplitude modulation for rectangular pulse shapes and seeing the spectrum where the side lobes were extremely high, we are designing the same system with a different pulse shape, which is a root raised cosine filter. So let's start with the basics. The title is PAM transmitter with RRC pulse shape, and the sample rate is 32K, sample per symbols are 8. And excess bandwidth, I've chosen 3 different values, 0.9, 0.5, and 0.1 to show the effects of either extreme and something in the middle. So this is our binary bits generation source. We are packing k bits where k is 1, which means that a symbol of 0 is mapped to a -1 and a symbol 1 is mapped to 1. We are not collecting multiple bits into one symbol yet. So character to float, again, as I told you that most of my flow graphs, you will see the flow will be here, and to keep the focus on the real deal, and the programming nuisances will be kept outside. It is still in the flow graph, but I have chosen the throttle and character to float out of the workflow. Here I'm looking at the oscilloscope output with the transmitter symbols and the upsampled symbols after interpolating it by a factor of 8. Again, this is a vector with 1 at time 0 and the rest 7 zeros, just to create an upsampling block. I could have completely removed this block and I could have chosen to interpolate by 8 here, but then it would not have been exactly clear what we are doing. This is the concept we followed from the lectures. So this is a new block here. Instead of a rectangular pulse shape as before, with 4 ones, we have a root raised cosine filter. So I have given the gain as sample per symbol. You can see this detail in the text. And sample rate, the symbol rate is sample rate divided by samples per symbol. Samples per second divided by samples per symbol, which is symbols per second. Alpha is the access bandwidth controlled by this GUI chooser, and the number of taps I've chosen is 10 into sam per sim plus 1. So the group delays on either side is 5. We look at the output and the spectrum. Let's run the flow graph and see what happens. We can see that for an access band of 0.9, the transmit symbols, obviously they are already +1s, -1. The upsampled symbols are those +1s, -1 with 7 zeros in between. The RRC filtered waveform is much smoother as compared to the rectangular pulse shape. And due to this smoothness, you can see that the spectrum, the side lobes are way below the actual spectrum. This is what we have achieved by smoothing out the transition between these two symbols. We have chosen a better response for the side lobes. What happens if we choose an excess bandwidth of 0.5? We are not giving much extra bandwidth to the spectrum, and with the value of zero point 0.1 we have larger swings in time domain and the spectrum is filtered in the frequency domain in zero point 0.5 and 0.9. This is a pulse amplitude modulation flow graph with the root raised cosine pulse shape. The transmitter details are as before, but we have included them here so that we can put oscilloscope and observe the spectrum at multiple points. Bits generation and lookup table from -1 to 1 upsampling and root raised cosine filter with the sample sim is a gain and the symbol rate is as discussed before, sample rate divided by samples per symbol, and the group delay is 5 symbols. On the receiver side, now we see that the match filter filters the incoming signal, but I'm not including any decimation here. I decimate the signal in here so that I can have the ability to decimate it at a different timing offset if I want to. So skips a certain number of samples before and keep one in n is the sample per symbol, and is in this case with this value is 8, which we define a variable here, and it throws rest of the samples. Let us run this and see what the output comes. Let us observe this one by one, and we'll see that these are the transmit symbols, the upsampled symbols which are doing nothing but inserting zeros in between every two symbols, the RRC filtered waveform, and the transmit spectrum. On the receiver side, after match filtering, you can see the spectrum is in a much more smooth shape. The waveform after match filtering therefore is different than the waveform after the RRC filtered part. And here we can see that on each symbol instant we can take a decision out by decimating. This is exactly what we are doing, and we are taking samples after every 8 samples, and these are the ones which match to the actual transmitted symbols. A scatter plot is the mapping of these samples to an IQ graph, and this +1 goes here, this -1 goes here. We'll discuss the scatter plot again in a separate flow graph.